Welcome back everyone to Data Science for Everyone. Today we're going to be talking about variation. So let me actually put that in here as a comment. Variation. Now, variation is the tendency of values of a variable to change from measurement to measurement. Now, we can see this in our real life, okay? Again, if you measure any continuous variable twice, again, you will probably get two different results. Now, this is going to be true if you're measuring quantities that are constant, okay? So each of your measurements, okay, is going to include the small amount of error in there, okay, and the variation from measurement to measurement. Now, categorical variables can also vary, okay, and again, this is going to vary against different subjects, okay. For example, we have different eye color. All right, we also have different times, okay. So this is like again, energy of electrons, or we have runners running a race, okay. Now, every variable, again, has its own pattern. And again, this variation is going to be very useful and is going to give us interesting information. So let's talk about also visualizing distributions. That's going to be the first thing that we want to look at. So we're going to visualize distributions. Now, first thing that we actually want to go on and do here is grab the tidyverse. Okay, and then we're going to go on and we're going to take a look here at the diamonds data set. And let's actually just glimpse this and take a look here. So again, we have a variety of data here. And again, if we see about this, we're probably going to have to look at, again, categorical data. There's a ton of categorical data here, okay? We do have some continuous data, and we'll look at that in a minute. But we'll start out with looking at some categorical data. So we're going to use ggplot here. And we're going to use the diamonds data set. And we are going to do a geom bar, and our mapping is going to be, what is our aesthetic going to be here? We want X to be, we'll use cut. Oops, cut. And so we can see now that we have a nice distribution here. Now, what this actually tells us is the height of the bars is going to display how many observations occurred in each X value. So for here, we're going to look at the cut distribution. Now, another thing that we can do if we want to actually get these values themselves instead of having this visualization here, we can go on and do something like diamonds here, count cut. Okay, and so here using this again, this here is actually a dplyr function here, count, is going to actually give us each of these counts by themselves. So here we have fair, good, very good, again, and they kind of go up, or they have them in descending order here. Now, another thing that we want to look at, and again, this was a categorical or discrete variable. Okay, now we are going to also want to look at a continuous variable. And so again, this can take basically an infinite number of values. All right, and again, they are ordered values at that. Now, this is, for example, numbers and date times, okay, are two examples of continuous variables. Now, let's discuss maybe our distribution of a continuous variable, and we would do that with a histogram. Okay, so let's go on and do ggplot here. We're going to do our data here is going to be diamonds, and then we are going to do a geom histogram. Our mapping here is going to be with our aesthetic here. X is going to be caret, and we're going to set our bin width here to 0.5. And so if we take a look here, we can actually go through and see here that this is definitely has a bit of skew to it, okay? Because again, there's probably some very high values up here at 4 caret, maybe even 5 caret, but we can't see them very well at this moment. What we can do though, if we actually want to see these values, is we can go on and compute these by combining the count and the cut width, okay, functions. So let's do something like diamonds. Here we want count and cut width, and then we're going to do caret, and then here is we're going to re-put in the bin width here of 0.5. And we run this, and here we can see here that we have all of our, these are our bins here, okay? So that is basically this point to this point right here, this point to this point, this point to this point, this point to this point, okay? And you can kind of see them all the way down. There's even one right here. You guys probably can't see that very well on your screen. But we do have, again here, all of our bins, and you can actually see what the count is per each of those bins, and you can actually look at how these bins are created, what their actual widths are. And this is very useful for us. Now, what this says here is that this is actually bounded, okay? So it actually includes negative 0.25, and it does include 0.25 here. It excludes 0.25, and it goes all the way up to and including 0.75. So this is the size of the caret. Okay, so again, notice here there's even some of these giant carets. I mean, again, these diamonds are probably size of a quarter or bigger. So let's actually talk about what's going on in this histogram. Okay, the histogram itself is actually divides into an x-axis into equally spaced bins. All right, now then again, it's going to be the height of the bar is displayed the number of observations that fall into each of the bins. Okay, and that's so here, this tallest bin here is going to have almost 30,000 observations, so 29,498 observations of the value caret. And again, that is going to be between 0.25 carats to 0.75 carats. And again, that's from the left to right edges here. Now, we can also maybe look at how do we want to deal with this bin width, okay? So changing the intervals of our bin width is going to actually change in the units of the x variable. Okay, so we should always kind of explore a variety of bin widths when we're working with histograms. Again, as different bin widths are going to actually reveal to us significantly different patterns. Okay, so let's actually go on and take a look at this as well. So let's create a small data set for our diamonds here, and we have something like a filter here with a caret is less than let's do 3. Now again, I'm sorry, but that still a 3 carat diamond's massive. But what we are doing is getting rid of those some of these massive outliers here. Okay, so it'll help with our distribution. So then we can go through and do ggplot. ggplot here. Data is going to be small. Oh, and you know what? We'll set our mapping here to aesthetic here. X is going to be caret. And then we want to go on and do a geom histogram here, and we are going to set our bin width here to 0.1, okay, to make this a little bit smaller. Now notice, okay, we got rid of an outlier, and then we made these smaller bins, and notice here, it just kind of exploded for us, all right? Now, maybe we want to, one very, very useful thing, okay, is maybe we want to actually layer a couple histograms together to get a little bit of a differentiation in them. And again, we can see here that this is definitely a zoomed in view of what we had before, okay? So again, you guys can kind of make up what you think about this. Again, if you notice here, there's a bit of a pattern kind of going on here between each of the half carat intervals, okay? So here's 0.5. Again, notice there's a ton of half carat, probably 7.5 here, something like the 1 carat, the 1.5, and the 2. Okay, so people want that whole carat setting usually. Or maybe that's just how they happen to be cutting them, etc. Again, they're cutting to fit usually. So now there are some issues, okay, whenever you want to maybe have a bunch of overlapping histograms and that type of stuff, we usually say that you should probably use something like a geome frequency. Okay, and this is going to actually perform the same calculations as a histogram, but instead of displaying counts with the bars, it's going to be using them as lines instead, and it is significantly easier to read. So let's go on and take a look at that. We'll do ggplot here, and I'm going to go on and use this small data set because, again, it's significantly easier to read, and we get a little bit more meaningful values out of it when we look at it this way. So we'll do X here is going to be caret, and our color here will be cut. And so we want to do a geome frequency poly, and we will have our bin width. Whoops. Bin width here we want to be 0.1. Okay, and so here there are going to be a few challenges again. So maybe the coloring's not very good for you, something like that. But you can go on and try and kind of play with that a little bit. But here you can actually see we can look at the distribution based on the cut itself. So again, whether it's a fair quality, again, there's a lot less of those. And again, the ideal, there's significant more, but they do have a tendency to be, again, these smaller bits of diamond here. So now that we can kind of visualize these variations, we kind of want to talk about, for example, typical values. It's always going to kind of come into what is a typical value. Now, both bar charts and histograms, again, the tall bars themselves are going to be the most common values. The shorter bars are going to be the less common. So let me pull this up, okay? So again, these higher bars here are definitely going to be the more common values. The smaller bars are going to be the less common values. Now, places that the bars do not have these, they don't necessarily reveal values of where they're not seen, okay, in your data. So which value, for example, we can always ask these questions in our minds, all right, and turn this information into useful when we have these useful questions and turn this information inward, okay, and actually express them outwardly as well. So which values are the most common? Why? Again, so when we looked at some of these values, okay, we can kind of tell, all right, that these cuts are probably more common. And if you notice, we have some of these little bit of trailing off areas here, okay? And again, maybe which values are rare, all right? Now, do we see any unusual patterns? Again, all of these things are very interesting, but let's take this one more, okay? Now, I'm going back to our basic histogram. I'm going to use small again. We're going to do this on caret, but I'm going to change the bin width to 0.1. Okay, I'm making it even smaller, and notice what we have here. Okay, there is definitely this very cool kind of wave pattern happening here. So again, why are there more diamonds that are at the whole carets and common fractions? Okay, well that's kind of just usually how humans measure things. Why are the diamonds maybe slightly to the right, okay, of each peak? Because notice here, okay, we have these high peaks, and then they kind of narrow down, all right? But again, there's definitely, they have this low area here, right? They kind of have these nice straight lines. Maybe it's how they cut them. I don't know. Again, I don't specialize in diamonds or anything like that, but I can kind of guess. This is where you would need to go and ask an expert, okay? Go to a diamond cutter and say, hey, what's going on here? Now, why are there usually no diamonds bigger than 3 carats? Well, here's the thing. We know that we actually cut off some of those larger diamonds because we actually did that ourselves. But again, it means that those are probably exceedingly rare types, okay? We also see that there is a little bit of clustering, okay? Or similar values that suggest there are subgroups that exist within our data, okay? So you can kind of see that there are definitely some clustering going on in each of these, okay? Now, how are these observations within a cluster similar to each other? How are they going to maybe separate them out? Again, these are questions that we really need to kind of look at. And one of the best ways to actually do that is to take a look at the old faithful Yellowstone data set. And so let's go on and actually kind of dig into that. So let's do oh, you know what? Let me actually go on and say faithful. And we can actually, whoops. Let me clear that and do glimpse of faithful. And notice here we have just two variables here, okay? We have eruptions and waiting. Again, this is usually the number of people waiting. So what are we going to actually see here, all right? So let's do ggplot here, and we'll do data is equal to faithful. And then we want in here, we will have our mapping is going to be, X is going to be our eruptions. Okay, and then we also want to do a geom histogram, and we'll do our bin width here of 0.25. And let's actually take a look at what happens. Notice, we got two primary, this is what we call a bimodal distribution. Okay, we have kind of two main groupings, okay? This main grouping here and another main grouping over here, okay? We have these two sides to it. Now, this kind of prompts us and say, what is the relationship between the variables, what's actually going around here? Now, what we actually know, okay, is the eruption times appear to be clustered into these two groups, okay, this bimodal distribution. And there are short eruptions, okay, that's these here, okay, of around 2 minutes. And then there are long eruptions over here of 4 to 5 minutes, okay? And then there's very little eruptions in between. So again, this is fantastic for what we are able to kind of look at. Now, the next thing that we kind of want to do here, all right, is start looking for unusual values. Now, to do this, okay, we definitely need to go back to our diamonds data set. So let's do ggplot, and let's do our data is going to be diamonds. And we actually are going to look at the histogram mapping here, and we want this actually to do this on kind of a weird variable here, okay? We're going to do this on y. Now, and I'll talk about that in just a second once I plot this out. We want our bins, our bin width here to equal, oops, oh, that's why. Bin width here is going to be 0.5. So let's actually kind of talk about this just a little bit. Now, unusual values are called outliers, okay? Now, these are data points that just don't seem to fit the pattern, okay? They are weird in some way. Now, sometimes outliers are erroneous data, okay? Now, other times, though, outliers suggest a very important new science, okay? Again, I personally get very excited when I see outliers. I want to investigate, okay? Particularly if I know that it's not an incorrect measure. Now, when you have a lot of data, okay, outliers are something difficult to see in a histogram. For example, okay, take the distribution of this y variable here that we have in our data set. Now, the only evidence of outliers is that there are unusually wide limits to the x-axis, okay? So notice here, we have all of this area way over here. Again, yes, I know that it's called, the variable is called y, but this is the x-axis, okay? So there are some extremely uncommon variables in here because, again, we don't see anything here. Again, we have so many. We have more than 12,000 count here. But notice here, this from like 20 to 60, we don't really know what's going on. So we can actually go through and really dig in to see what's happening here. So we can retake our histogram here, and we can use our coordinate Cartesian to actually kind of zoom in on those values. So coordinate Cartesian, and here we want our y limit here, and we're going to say that we want it to be from 0 to 50. And let's take a look. Oh, now notice what we have here. We have these two little pips, okay, coming in here. So what's happening is we are using our coordinate Cartesian to limit. Now we can also limit, for example, the x-axis, we can also limit the y-axis. Now we limited the y-axis here because what we did is we kind of squished everything down a little bit. We cut off. We didn't want to see all of that 1200. We know that there's tons of numbers that are way up there, but we wanted to see and zoom in and see, oh, what about these values here? Okay, it does also have an x limit for you guys. Now this is going to allow us to kind of see that there are definitely some values that are interesting here. So probably somewhere around 30, and again, some here very close to 60. So what do we want to maybe do with this? Okay, let's actually kind of pluck out those numbers and take a look. Okay, so we want to actually take a look at our unusual values. And I'm going to call this outliers. How about that? And we want diamonds here. We want to filter everything, or y is, and again, notice here we have some small values here too. So let's go on and do something like y is less than 3 or y is greater than 20. And then we also want to select out here price x, y, z, and then we want to arrange them by y. And then let's actually take a look at our outliers. So notice here we got quite a bit of interesting things going on here, okay? So this y variable measures, again, one of the dimensions of the diamond itself, because again, it's think about a diamond as a three-dimensional object, okay? And this is in millimeters. Now, we know that diamonds can't have a width of 0. Notice, look at all of these, okay? So those values are incorrect. Now, we might also suggest that maybe this measurement of these larger measurements, okay, like for example, these high values. So for example, this these values up here, okay, so that would be something like here. Notice this here is 30, almost 32 millimeters, and this one's 59 millimeters. Okay, maybe they're implausible. Okay, so maybe so those diamonds are, again, they're like an inch long or longer, and again, they don't cost hundreds of thousands of dollars. So probably we could say that these are probably misrepresentations, mismeasurements. So again, this is something that what I would wind up doing, okay, is removing these outliers, okay, and then go through and redo all of the analysis that we had done before, okay? Because again, we are pretty sure that these variables are erroneous in nature, okay? So we don't want to actually hold those inside of our data set, okay? So I'm going to leave this here. I hope you guys like this. If you did, please comment, subscribe, and hit that like button, and I'll see you guys next time. Bye-bye.